All right, so questions? Sounds like a question, yeah.
So I found out how to do the ODP for string length.
Mm-hmm.
And I worked out using like arrays and then pointers. And I was able to, for some reason, it wasn't like outputting any number, like not even the address or any numbers. No.
Okay. Yeah, if I can look at your actual code, we can talk about that. But let's talk about the ODP more generally first. So here's a version of this function that'll do what we need it to do. And I chose to treat this thing as a string, so I'm using string length to see how many characters to deal with. So I'm including string.h, declare the function, takes a char pointer, returns an int, c is a running counter, initialize that to 0. And then my for loop just says for I equals 0 up through string length -1. If character I of arg is equal to an e, increment c, and then return c. Okay. And there's 4 lines of executable code here, right, which makes it look pretty simple. But there are, at least a dozen ways that you can go wrong with this, possibly more. And when you see a piece of code that works, right, it tends to look pretty straightforward. But there's so many slight changes that you can make to this that will, in some cases, do very different things. And so this doesn't really tell you what you want to know about ODP 413, right? The question is, if you didn't get this to work, or if it took, a lot of tries, when you wrote a version of this for yourself, right, what did that version do? And if it wasn't doing the right thing, if it wasn't assessing 100%, right, what was it doing? That's the code you want to study, right? Not this, because this is pretty information poor. So let me look at some other versions of this. So here's a version that that uses a while loop. So while the arg I is not the null terminator, if arg I is e, increment our counter c, and then increment I, which is the index, and at the end of the loop, go back and return that value. And I have my unexciting test program, which just calls count e on a fixed string, EIEIO, and prints out what the value of I is at the end. And so if I run this, it tells me I equals 2, right? And that's what you would expect. But let's look at some versions of this. So here's a really easy way to write this, intending it to do the same thing, but I put the I++ and the curly bracket in a different order, right? And I can compile that, and if I run main, it doesn't come back, right? Now, if you're assessing your program, it looks like you said G and you hit enter and nothing happens, right? It's just kind of hung up. But before you're assessing, you should have tried this on your own main program, and you'll probably see similar behavior, which is it never gets to my print statement, right? My main program says call count and then print out the return value, and that doesn't happen. So that tells you there's an infinite loop somewhere, right? That's the most likely thing that's happening. So we want to debug this. So I'm going to say recompile all of these with a -G switch. And now let's say gdb main. And I'll say start. And I'm about to execute this call to count E. So I can say step to say step into that function, and now I'm inside my count E function. Okay, so let me list the source code for that. And first thing I can do is look at arg, and arg is my string that I'm expecting. That's good. So let's go ahead and start stepping through this function. So I've set C equal to 0, and if I print C, it's equal to 0. If I print I, it's already 0, but I'm about to initialize it to 0. So that sets I to 0. And now I can look at arg bracket I, and I can see that's the letter E. That's the first character in my string. Okay, so my while loop says, well, character I of my argument is not the null terminator, and I just checked it's not the null terminator, it's the letter E. I expect to go on through my while loop now. So if I say next, sure enough, I come down to line 7, and it says if arg I is equal to E. And we expect that that is true. So it should go into the body of my if statement, and it does. So it's about to increment the variable C. So let's print C beforehand. Let's go ahead and execute that. Let's print C again. Okay, my count got incremented to 1. So far, this is great, right? It's about to increment I. What's I equal to right now? It's 0. If I do that increment, I print I is 1. Okay, it looks like it's working exactly like it should. So now let's print out arg bracket I, and that's the letter I. Right, our string was E-I-E-I-O. So that's not the null terminator. Again, I expect to go into my while loop. And now it says if that argument is equal to E, and it's not. It's the letter I. So I expect to skip my while loop, my if statement. And now I'm back to the top of my while loop. And I print the value of I, and I is still 1. And I print arg bracket I. And it's still the letter I. Now my string was E-I-E-I-O. So we saw the E, we incremented our counter, we saw the I, we did not increment. I want to be looking at that second E now, but it looks like I'm looking at the letter I again. And if I say next, it'll say if that's equal to E, which it's not. So I go back to the top of my while loop, and I look at I, and it's still 1, and I look at arg I, and it's still 1. And right now, if you're following this, right, which is hard after a few hours of this, but if you're following it and you're thinking about what's happening, my variable I is never changing. I keep checking the second character of my string. It's not a null terminator, so I go on. It's not the letter E. I don't increment my count. I go back to the top of my loop, and I check the second character of my string again. And if I just keep saying next, right, there's my infinite loop. So now you look at your code, and this is nicely indented. If everything's sort of flush on the left column, it can be a little harder to pick this stuff up. But with the indentation, it kind of jumps out to you that what's happening here, well, exactly what I told it to do. If the argument is not the null terminator, go into here. If it's not the letter, if it's the letter E, do these things. Otherwise, skip all of this. So my while loop checks to see if it's the letter E. If it's not, just goes back to the top of the loop. So there it's pretty apparent, oh, what's going wrong here is that I need to increment I, whether this is the letter E or not. Okay, so we kick out of here. And now we've got a few options. Right, so this will work, and that might be what our train of thought leads us to. So if the argument's an E, we increment the counter, we increment I, otherwise we just increment I. And that'll work perfectly well. But since we're doing this statement, whether the if statement is true or false, we could also just move it outside the if statement. And that might be a little clearer down the road. But this will work just as fine. Right, so now it tells us we have 2 E's in there. But we could also do that. So the whole goal of debugging is you've written your program to do this, but it's not doing this, right? So you want to figure out what is it doing, and putting in lots of print statements, is one way to tell that. Running it inside a debugger is another way to tell that, right? Now, sometimes the debugger changes things and it can actually make it harder to see what was going on. But usually, popping into GDB is a pretty good way to see what's going on. And it feels kind of awkward the first few times because we're not used to stepping through programs, and if you say step instead of next, sometimes it does weird things and so on. But with practice, right, it becomes pretty natural to work inside here, and then it's really valuable. And you want to be comfortable with this before you get into 222. Because 222, if you can't use GDB, there's very little hope, right? It's just a big black box, and you don't really know what's going on inside. And trying to use print statements for that is pretty unpleasant. So the better you get with GDB, the more success you're going to have. Did I post a video on GDB on Canvas? Yes, I did. There's a command summary. All right. So, I thought the checkbox meant that was selected. It was not. Okay, there we go. All right. So this is like a 10-minute GDB video I put together a few years ago for some students from Clark who were at WSU, and they were struggling because they hadn't learned GDB well enough here. And so I just kind of like sat down. I went through a few commands. It's about 10 or 12 minutes, I think, and posted it on YouTube. And it's like by far my most watched video. It's got like 100-some thousand views on it. And I've got all these artsy videos that I spent like weeks, putting together clips, and I composed music for and stuff like that, and they get like 10 views. So, it seems to be well received. If you want just kind of an overview run through from start to finish of using GDB to dig into a C program, it's not a bad look. So that's got a link up to it now. So practice with it, right, and you'll get there. All right, so questions about that? Yeah?
What does the plus plus on the left side of the variable mean?
Same thing as on the right side in this case. So if you have an integer and it's got some value, if I say plus plus I, it basically means set I equal to I plus 1. And if I say I plus plus, that also means set I equal to I plus 1. Okay, but if I say something like x equals plus plus I, that's the same thing as the following. I equals I plus 1, x equals I. But if I say x equals I plus plus, that's equivalent to the following. X equals I equals I plus 1. So the difference, in both cases, I ends up being incremented by 1. The difference is x equal to the new value of I or the old value? Right? So if you put the plus plus on the left, it says first I want you to increment I, and then I want you to set x equal to that new value. If you put it after, it says first I want you to set x equal to I, and then I want you to increment it. Neither is necessary, right? You can always say I equals I plus 1. You can say x equals I before or after as you like. But C equals C plus 1 is 5 characters, plus plus C is 3 characters. It used to be this would compile into faster code because compilers weren't very sophisticated, and most systems, if you use the PIC processor, it has an increment instruction. right? And increment is easier to use than add. You can just say increment file register and name the register. If you want to add, you got to move a literal into W, you got to add W to the file register. So in the old versions of the C compilers, if they saw this, they would code that as increment file register C. Whereas if you said C equals C plus 1, they'd say move literal 1 into W, add WF to C, and it would take twice as long. Now it's mostly just kind of a shorthand. So there were a few cases where people wrote this ODP and they were looking for the new line instead of the null terminator. Okay, strings do not have to have a new line in them. Okay, they can terminate, they can contain or not contain a new line. Now, if you read a string from fgets, chances are it's got a new line tacked to the end. Okay, but if you just got a string like quote EIEIO, there's not necessarily going to be a new line. So suppose you write your program like this, and the rest of this code should work. So I'll step into my county function, and I'll start running through this. And so I is up to 4. And I'll print I. And this character of my string is the null terminator, but I'm checking for a new line. So let's just keep going through this. And it's just flown past the end of my new line now, right? And it got into, oh, it returned, okay. So you may get lucky. It may be that there's a null terminator somewhere shortly after the end of your string, or a new line shortly after the end of your string. So let's see what our string actually looks like. Interesting. Anyway, I don't know why it's not like just dying in a seg fault, but just finding a new line somewhere. So yeah, strings are defined to end with a null terminator. That's the only guarantee. Okay. They may or may not have a new line. They may or may not have spaces. They may or may not have anything. Right? The first character could be a null terminator. If you go beyond that null terminator, you're in risky territory. Okay, because you might encounter who knows what, dragon stuff. And if there doesn't happen to be whatever you're looking for off in future locations, you might actually go into a location of memory that you don't have access to and you get a seg fault. So that's another potential issue. So I did not post an ODP today for tomorrow. I will post an ODP later tonight or this afternoon, and it'll be due on Friday. Okay, because I want to give you time to work on it ahead of time and then ask questions in class tomorrow if necessary. It'll be another exercise in working with strings. But I want to make sure that people have a chance to actually get that completed. Bless you. All right, so questions on 413? All right, let's go back to this business of modularizing code. So we took this yesterday to the point where we had our main program, main.c, and it was calling a bunch of other functions, right? And if we look at main.c, it's calling my function start, it's calling my function show6, and it's calling play game. And I haven't typed in any prototypes for those functions anywhere, but the compiling doesn't complain about that, right? That's because I have an include statement here which says include this file stick.h, and stick.h just sets up my function prototypes. So what does include actually do? When you've got a program and you say number sign include some file, and it could be in quotes if it's in your current directory, it could be in angle brackets if it's in the system directory. But when you include file, basically what the system does before it does any compilation, it takes this line, it removes it, and it replaces it with the contents of that file. And now the program that you're compiling is bigger than the original program because this line has been replaced by whatever is in that file. If there's 1,000 lines in this file, your program has just grown by 999 lines because those 1,000 lines have replaced this one line. So we don't usually put C code inside these include files. Our goal in modularizing, and we're going to see this shortly, is efficiency. We don't want to compile every line of C code we've written for our program if we've only made a change in one piece of the program. So by putting these things in different files, we can compile one file and not have to compile the others. But if we include all of those files in our main, then every time we compile main, we're compiling basically the contents of every file we included. So don't include .c files. Okay, this is really important for efficiency. We include files that have things that we need to type in the beginning of our program. For example, the function prototypes that we're going to be using. Or if you had a number sign define, if you were setting up a symbol, like max number of sticks, right? So you might say define max sticks to be 1,000. And then I can use max sticks anywhere in my C code and it gets replaced by the number 1,000, right? So I can put an upper limit on this. So in fact, let's do that. So start. I'm going to make sure it's defined. Yeah, so to be clean, you'd want to make sure it's not defined before you define it. And you wouldn't want to use it unless it's defined. I'm not going to go there for this. But yes, you're absolutely right. So I'm throwing some code into main. And let's make our maximum number of sticks 100. So this is the old-fashioned way of compiling. Just take all my C files, compile them, link them together, make my executable program main. Let's see how many errors I got. I knew I'd get errors. All right, so now if I say main, I can play my program the usual way. If I say main 101, it says too many sticks maximum, right? Okay, so your include files are things that you would normally type in the top of your program, right? Or the middle of your program, maybe. We include stdio.h because it tells us the prototype for printf. It tells us the definition of null, the definition of eof, right? All of these things that we use are set up for us in standard io.h. But the code that comprises printf or fgets or scanf, that .c code is not part of stdio.h, right? Because we don't want to compile all that stuff every time that we want to run a program, just because we want to do a print. So standard io.h mainly includes function prototypes, okay, but not the actual code. So the things that you include should contain prototypes, defines, right, not the executable code. And conventionally, include files are called .h. They don't have to be. You could call it anything you want. You could call it a .c, but that's a really bad practice, because usually .c means C source code. And even though this is source code, it's not executable. All right, so here's the idea. We can compile this with big, long, monolithic GCC command. And this says compile, get user move, compile main, play game, show stick, start, and then link them all together and make an executable. But that's inefficient. So here's our main program, main.c. Here's our number of stick processors, start.c. Here's our show sticks .c, and there's other ones. So if we say gcc-c, these things don't turn into executable code. They turn into what are called object modules. They are machine ingestible versions of our original C files. So main.c has big long variable names, it's got comments, it's got white space, it's got curly brackets to mark the beginning and end of loop bodies or if statements, and it's got all this stuff that make it possible for us to read and write this program. But that means nothing to the CPU. The CPU wants ones and zeros. So these .o files are ones and zeros, plus a bit of extra stuff, right? But they've been scrubbed of the big, long variable names. The number of sticks we are playing with in this game, which is an integer, has been replaced by, hex 44, some memory location. So the .o files are very easy for the system to deal with. The .c's are fairly expensive. So this step is time consuming and possibly memory intensive. These .o's can get combined to create a main program. So these are called objects. These are called source files. And this is an executable. And the program that actually does this is load LD, but we can do it with GCC as well, because GCC knows how to link things together. So let's take a look at this. So here's what's in my directory right now. Let me get rid of main. So I've got .c files and I've got my h file. So I can say gcc-c main.c. And now I've got a main.o. So main.c is a couple of hundred bytes. Main.o is 1,500 bytes. My executable program is going to be over 10,000 bytes. Okay, but main.o is not the whole program. It's just the compiled version of main.c. And if I look at that, it's gibberish to me. It's got a little bit of English in it. It knows this was main.c that it came from. It knows this was built under Ubuntu, but it's mostly ones and zeros, a lot of zeros. But it's basically machine code.
What are those repeating triangles and the at symbols?
Caret at is usually a null. So So those \0s are nulls, and it's just the other stuff that's interesting. So it's not a whole lot of code in here. Nope, don't have it. All right, so here's what we can do. What did I miss? Get user move. All right, so now I've compiled by hand each of my .c files into an object. And now I can build my executable with the following. gcc-o main, and then I list all the object files that I want to compile into this executable. And now I've got my executable program again. And it's almost 13,000 bytes. So here's the thing. These operations, these compilations from C to .os, take a lot of time. This isn't really doing any compiling. It's just linking together all of these .o files. That's very efficient. So think again about a program that's got thousands of different files that all get linked together to make the executable. If I change one of those files, I can recompile it gcc-c filename.c and then re-execute this link statement that just puts all those .os together. That's very efficient. If I just recompile all my .c files and then link them together, recompiling all of that C code takes a lot of time. And in the most unmodular case, if everything is in one big file, my program.c, and it's got thousands of functions in it, and I change one line of code, the only choice I have is recompile that whole file. And it's going to recompile all that code, and that's very, very expensive. Question? So this highlighted line is not actually compiling anything. The .os are already compiled. All it's doing is actually linking. So GCC will do C compilation, but it will also do this linking together of objects, right? And even though I'm calling it with GCC, it knows it doesn't have to compile any C code, so it just calls LD and links those together. And that's pretty efficient. So now if I change my showsticks.c, so let's change this to print out my number of sticks in curly brackets. So I can recompile that. So that had to actually go through C code and translate it and build an object. But then I can rebuild my executable with just that compiling the .os, linking the .os together. And now I've got my stick list with curly brackets instead of square brackets. So this is a nod to performance, but it's not terribly convenient, right? This is not a very pleasant line to type in again and again and again, right? And if I introduce a new function, I have to put that new function on here. And if I've got thousands of functions, I have to list thousands of functions here. And I can get edgy and just say, star.o and hope that I don't have any .o files that don't belong in there. And it's not a very comfortable process. So there's a tool called make that will let us describe in one file how we want to build our program. And it will let us capture how we get these objects, how we turn the objects into an executable, but also if we have dependencies, it will let us capture those. So we want to talk about make files, and this is one of these things that It's the leaky roof problem, right? If it's raining and your roof is leaking, you don't want to go on the roof in the rain, right? If it's not raining, the roof's not leaking, I'm not going to spend time fixing it, right? And your roof never gets fixed. That's the problem with makefiles, right? If you've got such a big project that you need a makefile, well, it's a real pain to create the makefile because it's so complex, right? But if you're just starting your project and you only got 2 files, I don't need a makefile, I'll just say GCC, right? So a lot of times makefiles never happen. So it's really, really hard to sort of motivate yourself, but if you start from the beginning of a project creating a makefile and then update it as you go through, it will end up saving you time. So let me show you the basic setup of a makefile. So it's called makefile with an uppercase M. It's just a plain text file, right? It's like stick.h or main.c. You can edit it with VI. And a makefile is a set of pairs of lines. So each pair consists of the following. There's a word, which we call a target, followed by a colon. And then there's a list of 0 or more dependencies. Things that need to exist and be up to date in order to create this target. And then the second line always begins with a tab, and you can't just use spaces or your makefile doesn't work, followed by a recipe, an instruction or set of instructions for creating the target. And then this just repeats. And you can have as many things in here as you want. So let's put together a makefile, and then we'll talk about what exactly it does. So let me get rid of all that stuff that we just did. And let me make a makefile. So the first line of my makefile, I'm going to put in the main target that I'm trying to build. The main thing I want to build is main. So I'll say main colon, and then I'm going to list all the things that need to be present in order to make my program main. All right, so I'm going to cheat. And I'm going to say, in order to build my program main, I need to have these 5 objects. And if I have all of those, I'm going to put in a tab, I'm going to say, here's how I build main, gcc-o main, and then I'm just going to name those objects. All right, so let me save that. And if I look, I've got my C files. I don't have any objects right now. I shouldn't have deleted those. Say what? Yes. By the way, in VI, if you say :set list, you can see unprintable characters. So Control-I means tab. So if you're working with these, set list can help. All right, so in my current directory, I have all 5 of my .o files that I'm going to need to be able to build main. So if I run this makefile, it'll say, okay, I want to make main. I need these 5 .o files. It's going to find that I have those, and then it's going to say, okay, let's execute this GCC command to make my executable program. So I'm going to say make main. Make is the name of the command, and when you say make space something, it will look in your current directory for a makefile, uppercase M, and if it finds it, it will look for a target that matches whatever that something is, in this case main, And here it should find this target main. It should say, okay, you've got all the dependencies, and it should execute this command to build the target. So I say make main, and it does this GCC, and it just built my main program. Okay, let's get rid of start.o. And let's get rid of start.c, because it makes it a little too smart for this. So, so I do not have a start.o in my directory anymore. Okay, now if I say make main, it's going to give me an error. It says, hey, you need a start.o in order to make main, and I don't know how to make start.o.
And it tells you stop.
And it says stop. So there's no start.o in the directory. If it knew how to make it, it would make it for me. But we haven't put a target in here for start.o. So here's what we can do. We can make a new target, start.o. And to make start.o, we need a start.c. And start.c also needs stick.h. So we need start.c and we need stick.h. And if both of those are present, we can compile start.c to create start.o. How do we do that? GCC-c start.c. So now if I say make main, I don't have to keep saying main. If I just say make, it will make whatever the first target is, which is main. So I can just say make. And it knew that it needed start.o, and it searched through the make file. On that second set of lines, it found a recipe for start.o. It had start.c and stick.h, so it executed GCC-c start.c. That gave it start.o, and then it went ahead and it built main. And if I say make again, it'll say I don't have to do anything, everything's up to date. But if I edit start.c, and I haven't changed it, but I changed the date on it. So no start.c was updated at 1144, and start.o was updated at 1143. It knows that even though there is a start.o in here, it's not the most recent version. The thing that it depends on, start.c, is more recent than start.o. So now if I say make, it's going to recompile start.c for me. So if you construct your make file correctly, you never have to think about what gets compiled after that. Anytime that you make changes, you can just say make, and it will compile whatever has to be compiled. It will link whatever has to be linked. So it saves you a lot of time, it saves you a lot of thought and a lot of distraction. Because you don't want to try to remember how do I compile my programs into my executable. You want to write code, right? So every time you write code and you're ready to build your executable, you just say make, enter, right? But you got to set it up front. And it's easiest to do in the beginning before you have a lot of different files. We've got a lot of different files. So let me just go ahead and try to make short work of this. So what do we have? We have main, we have play game, we have show sticks, and we have get user move. Okay, so there's a good make file. Get user move does not need stick.h. It doesn't call any other functions that I've defined. So get user move, I'm actually going to get rid of this dependency. And show sticks also does not need stick.h. Main does not need stick.h. Right? The way that I'm building main is I'm just compiling these objects together. the objects have nothing to do with stick.h. Stick.h was part of how I turned start.c into start.o. But if I've got a start.o, I can delete my stick.h and still build my executable. I wouldn't do that. But I could, and this will still work perfectly fine. So this is not dependent on stick.h. But these GCCs of C programs, in some cases, depend on stick.h. Okay, so what can I do now? I can get rid of all my objects. I can get rid of my executable. I have nothing in here except my 5 C files, my include file, stick.h, and my make file. And I'm ready to compile. I can just say make. And it compiles each of those things into objects, and then it links them into an executable. And if I say make again, it tells me everything's up to date. Now I can use touch to just update the access time on a file. So I can touch show sticks. And now if I say make, it'll say, hey, showsticks.c changed. Let's go ahead and recompile that. Let's link everything together. Now if I make a change to stick.h, let's say I change the number of sticks to 40. Now I say make. Well, it didn't compile every .c file, because not every C file depends on stick.h. It compiled my main program, my play game, and my start.c, and then it linked those together. And if I try to make again, it's up to date. And now if I say main 50, it tells me the maximum number of sticks is 40. So we're back to really rapid development cycle, right? Got something to change in your code, make the change, say make, and you're done. Test your program by saying main, and you can just go from there. There's other things we can do in main. I don't want to rush through them. But for example, if we want to do debugging, we need to add a -G switch on all of these GCCs. Well, we can define a symbol up in the beginning here called switches, and we can use that symbol in these GCC commands. And if we set switches to nothing, it'll do this. But if we just change our make file and set switches to -G, and then say make, it'll recompile everything with a -G switch, and now we're set for debugging. And we can do that, and then when our program is debugged and we're ready to release it to the public, we go into our make file, we set that flag to be nothing, and we say make, and it rebuilds everything without the debug. So we'll play with a few more of these embellishments tomorrow, and then we'll go on from there. So I'll post ODP 414 later today, but you'll have basically a day and a half to do it. It won't be due until Friday morning. So look at it, start it. If you can finish it, great. If not, bring questions tomorrow. I will see you next time.